Welcome to Aeronautic Engineering 212. My name is Mr. Sack.
The idea
And here's the density equation. The density equation is D equals M over V, or mass over volume.
The idea
I gotta get back home.
And here we can see the yaw of the quadcopter.
I know. I can use the parts from a silver rocket to make a drone, and put a message on it, and fly back to civilization. I could build a quadcopter, an RC device containing 4 rotors. Here's how it could work. Propeller blades in the shape of wings connect to the rotors. With this shape, according to Newton's third law, the drone pushes the air down and the air pushes the drone up. A drone can also fly through the creation of differential pressure. The drone creates a low pressure zone above it by forcing air down. The low pressure below the drone causes the air to travel to the top due to its lower pressure. This creates lift. The rotors can help the drone with getting up and down by creating a decreasing lift, but now I need to think about maneuverability and thrust. These arrows represent the way that the propellers are spinning. As well as giving thrust, the motors possess torque, and when they are up in the air, there is nothing to oppose this torque, except for slight friction. So then this is why 2 of the motors spin in the opposite direction, to oppose the torque of the other motors and vice versa. The drone moves along 3 degrees of rotation: yaw, pitch, and roll. Yaw, the rotation of the drone about the z-axis, is increased by applying force on the rotors spinning in the same direction, motors 1 and 4. In order to increase yaw in the clockwise direction, make the copter rotate clockwise, rotors 1 and 4 must increase in force. This increases the torque in the clockwise direction, and hence the drone rotates clockwise. Pitch is when the front or back portion of the drone is raised or lowered or rotated about the y-axis. In order to increase pitch in the front of the drone, propellers 1 and 2 must spin at a higher velocity. In this diagram, the drone would fly in reverse. Since propellers 1 and 2 spin at a faster rate than propellers 3 and 4, the torque that they produce cancels out and only produces pitch, raising the front half of the drone above the back half. Slanted upward, the drone will move backwards. Roll is rotation about the x-axis, except it is rotors with 1 and 3 or 2 and 4. These 3 controls, including the rise/lower function, are created by decreasing and increasing thrust to all 4 motors. I remembered! I can actually calculate the max force that the motors can generate by using the lift equation, where lift equals the lift coefficient times the density of air times the velocity between the rotors in the air and the surface area of the propellers. This equation represents the differential pressure part of lift. The other part of lift, involving Newton's third law, can be determined when I calculate the volume of air that is being displaced. Now on to the hard part, the building. The drone should definitely have first-person view video capabilities. I should put a camera in the front so I can monitor its surroundings as I pilot it. I can salvage some extra carbon fiber from my chip because it will be much lighter than metal. I'll need a small rectangular box with 4 arms for the 4 motors. That takes me to my next problem, the motors, or the legs of the drone. I can build the motors using a magnet with 2 poles with electromagnetic coils on all sides of it. The poles in the middle repel the electromagnets on the inside and cause it to spin 180 degrees, because the coils want to align with the magnet in the middle. The poles of the electromagnetic coils are then changed by an alternating current. This alternation in current causes them to rotate again another 180 degrees to align. They then continue spinning due to the constant change in current. Now, I need a control system. The remote control sends a signal to the receiver on the drone. The receiver then relays this information to the flight controller, which creates a plan of attack by sensing the orientation of the drone using a barometer and/or gyroscope. Then, this plan is sent to the electronic speed controller. Very simply, I can build these electronic speed controllers by creating a circuit hooked up to each motor that has a switch on it that regulates the current flow by switching the circuit on and off very fast. This creates the alternating current which is needed for the motors to function. The LiPo battery provides a direct current, so this piece is essential. It can also regulate how much current goes to each motor so as to control the RPM and therefore the thrust. There are then two main organs left within the drone: the power distribution board and the battery system. The power distribution board receives power from the battery and distributes it to the electronic speed controller, the camera system, and the flight controller. The receiver receives power through the flight controller, and the motors receive power through the ESCs. The camera system functions as the eyes of the drone. The camera connects to the power distribution board and a camera receiver on the drone. This piece receives the video feed from the camera and sends it to my live video feed via antenna. Now to build. Once the drone is built, the motors, which contain the electromagnetic coils, are attached to a central zone called the stack, which contains the electronic speed controller, power distribution board, and flight controller. The flight controller is attached to a receiver which has an antenna to interact with the controller. Then, in the front, is the camera, which is hooked up to the camera receiver in the back. Calculations will then confirm whether the drone will work or not, and how well. I first want to find the volume of air that is displaced by my drone to keep it up. We must use the density equation. Density of air equals mass of air divided by volume of air. The density of air at sea level is equal to 1.225 kilogram per meters cubed. Thus, the only needed information is the mass of air and our variable, the volume of air. In order to discover the mass of the air, we must use the force formula that I have derived. The mass of the drone times the gravitational constant is equal to the mass of the air times the acceleration of the air. Basically, what this means is the force of gravity on the drone has to be equaled out by the force of the air on the drone. This equation represents the lift for the main way that my drone makes lift, which is through Newton's third law. The left side of the equation can also be understood as the force of the air on the drone, or the total thrust of the drone by the force of the air. In this equation, the mass of the air will be calculated by finding the acceleration of the air. A device called an anemometer will be used to measure the wind velocity beneath the drone throughout its liftoff sequence, which can be used to find an average acceleration. These separate velocities will be measured up at different times from the start. The time is to be found with a stopwatch from the beginning of the drone startup until the end. Velocity is measured when the anemometer changes values. These points can be plotted by time, velocity on a graph. In order to convert the velocity to acceleration, the formula acceleration equals final velocity minus initial velocity over final time minus initial time must be used. Once acceleration is found, it can be plugged into the force formula equation to find the mass of the air. Following this, the mass of the air can be plugged into the density equation, which as a refresher is density is equal to mass over volume. Once these variables are discovered, the volume of air can be found. The final answer is about 0.95 meters cubed. Now that I have the numbers for just hovering, I can calculate the numbers for when it is at an angle, let's say 10 degrees. I can draw out a diagram and fill in all relevant angles by simply using complementary and supplementary angles. In this diagram, I separate the thrust vector into the horizontal thrust and vertical thrust. Then I can find the hypotenuse, which is the total force vector of the drone, by taking the cosine of 10 degrees is equal to mass times the gravitational constant divided by the hypotenuse. Solve, and I have the amount of force needed to make the drone fly at this angle. I can then do the same method to find the volume of air as the last time. So, I just need to plug the force vector value that I just found into the previous equation. Mass of the drone times the gravitational constant equals mass of air times acceleration air. But I'm going to need to replace the left side of the equation with the force needed to fly at 10 degrees and solve for mass, and then find volume by plugging it back into the density equation. It looks like the silver bullet will fly.